Okay, this is our astronomy class for Monday, February 3rd. And last class we did somewhat of an introduction. We spoke about planet Earth. We spoke about the basic structure of what's out there. The Earth, the moon orbiting the Earth, the solar system, the Milky Way galaxy, etc. Today we're just going to talk a little bit about what many people consider to be astronomy, and that is, well, when I go out at night and look at the sky, what do I see? For most people, that's what astronomy is. So we just want to talk about a bit what we see when we look out. First thing, when we look out into the sky, we're looking through the atmosphere. And when we look through the atmosphere, that can distort or change what we see. Just like here on the surface of the Earth, if you look through a dirty piece of glass, you may not be able to read anything on the other side because the glass is really dirty. So that glass distorts what you see. Even if the atmosphere was clear and clean, which it's not, there would still be distortions due to the atmosphere. Let me just put a little diagram here to illustrate how thick the atmosphere is. So if this line represents the surface of the Earth, and you're standing here, and you're looking up into the sky, the atmosphere, now there's no clear absolute number to this. How thick is the atmosphere? But say I just use these blue lines to represent the atmosphere. The height of the atmosphere some people say it's 100,000 feet. Some people say it's 100 miles. Or there are other possibilities. You could say 120,000 feet or 150,000 feet. The point is, there's no exact number for how high the atmosphere is. But 100,000 feet would probably be the low limit for the height of the atmosphere. So when you go out at night, you're looking through 100,000 feet of air. Now, in the room where I am now, I can see the walls clearly. So I say, well, what effect does the air have? I can see things perfectly clearly. True, but I'm only looking through 20 feet of air. If I was looking through 100,000 feet of air, it's going to change the appearance. So, talking about the question, what do we see? We have to keep in mind that when we're looking through the atmosphere. two examples of changes that we see because of the atmosphere. So I'll just call this visual changes due to what is commonly called atmospheric effects. One, air is colorless but the sky is blue. A blue sky is an atmospheric effect. The air is not blue. It's what you see. Air is colorless. The sky looking blue is an example of an atmospheric effect. Later on in the semester we'll talk about that because that's a question a lot of people have. Why is the sky blue? There's a reason for that, which we'll discuss later during the semester. Another atmospheric effect the sun can look orange at sunset. So you could be outside in the summer, you could be at the beach, and the sun is setting. As it gets lower in the sky, it looks orange. The sun is not orange. If there was no atmosphere, the sun would basically look white. That orange color is another example of an atmospheric effect. Now, you wouldn't know that unless somebody told you or you read about it, because that's what I see. Same thing with the moon. Sometimes when the moon is very low on the horizon, a full moon usually, the moon can look orange. The moon is not orange. If there was no atmosphere, the moon would always look basically whitish yellow. That orange moon, again, that's due to an atmospheric effect, but I'm just putting the sun down here. Another example of an atmospheric effect. Stars don't twinkle. Twinkling meaning like they get brighter, then a little dimmer. That brightness flashes a little bit on and off, on and off. That's an atmospheric effect. If there was no atmosphere, stars would be on steady like a light bulb. They'd just be there. They'd be on. But because we're looking through the atmosphere, there's an illusion of stars getting brighter, dimmer, brighter, dimmer. But that's not what they're really doing. That, again, is an atmospheric effect. So there's just three examples of what looking through the atmosphere causes us to see that can be deceptive, because that's not what's really there. It's the effect of looking through the atmosphere. Another little point about what you see when you go out at night. Stars look like they look like they're stationary or standing still. So if the stars were out tonight and you went outside with a friend, or I went outside with a friend and we pointed to a star, I just point. I wouldn't have to move my finger, I just basically point. So it looks like the stars are stationary. They really are not stationary. They're actually moving at thousands of miles per hour. More often, it's tens of thousands of miles an hour. So that star you might be pointing to may be moving at 70,000 miles an hour. But it's weird because you say, doesn't look like that to me. I'm just pointing, just standing there. Yeah, but just like the sky looking blue is an illusion, stars looking like they're stationary, that's also an illusion. Not due to atmospheric effects, but due to the great distance. Except for the sun, which we've already discussed in class, all the stars are trillions of miles away. And when things are far away, they look slower. It's just a consequence of distance. And I can give you an example that's independent of astronomy. I can just take this eraser. I can move it right in front of me. I can go like this with it. To me, right now, this eraser looks like a blur. And most people say, well, if something looks like a blur, it must be going fast, because to me, that looks like a blur. It's not going fast. This eraser right now might be going 3 or 4 miles an hour. Now, compared to everyday things, that's not very fast, 3 or 4 miles an hour. It just looks fast. That's the illusion. If you went outside during the daytime and you saw planes flying around in the sky, and you did that trick again of pointing at a plane. So I said, oh, there's a plane, let me point at it as it's flying by. So you'd point at a plane and you'd kind of move your finger like that. It's going to look slow compared to a car going by. If you're standing on the side of Grand Central Parkway and the cars are whizzing by, and then you look at a plane flying, you move your finger, it looks like it's going a lot slower than the car. That's wrong. Plane might be doing 400 miles an hour. The car might be doing 40 miles an hour. Well, how come something going 400 miles an hour looks slower than something going 40 miles an hour? It's the distance. Those cars might be 50 feet away from you. The plane might be 5 miles away from you. Anything that's further away, the illusion is it's going to look slower. So if you expand this idea to trillions of miles away, even though the stars are going 70,000 miles an hour, they're going to look like they're standing still. But they're really not. If there's a message here, it's this. You have to be careful about interpreting what you see. Because you're definitely seeing something. You're definitely seeing the sky look blue. You're definitely seeing the moon look orange. You're definitely seeing stars that are still, but none of those things are actual reality. They're illusions. Another thing about what you see or what we see when we look out from the Earth, this is something, again, just like the sky being blue or seeing the moon. This is something everybody's familiar with. The phases of the moon. Sometimes the moon can look like a full circle of light, sometimes a half a circle, sometimes a little sliver of light. Again, anybody on Earth could notice that. And if you asked people, well, how come that happens? How come sometimes the moon looks like a big bright circle, other times like a half of a bright circle? Most people say, oh, that's because of the Earth's shadow. The Earth's shadow is falling on the moon. That is not true. I'll say a few words about what it is, and then I'll draw a diagram. The reason sometimes the moon looks full and sometimes it looks like a half a moon depends on where we're standing when we're looking, where the moon is, and where the sun is. So it's basically due to positions of things. So right now where I am, the parking lot for Vaughan College is probably about 100 feet away from me, which is not very far. I can't see it. I'm in the basement. There's a ceiling above my head and walls. So just because I'm 100 feet away from something doesn't mean I can see it if there's a wall in the way. So my position being in the basement changes what I can see. If a door is open or closed, that's going to change what I can see. If the door is open, I can see the cafeteria. If the door is closed, I can't. So again, my position is determining what I see. Now, here in a classroom, that's easier to get because I'm used to it. This is what a room looks like. If there's a wall there, I'm not going to look through the wall. If we take it into space and the solar system, if we were to say this, and let me emphasize, this diagram is not drawn to scale. It's way off scale. Let's say here's the sun. And here's the Earth. Let me label that. This is way, way, way out of scale. Here's the sun. The sun gives off light and heat. So it's giving off light in all directions. Half the Earth is going to be in daylight and half is going to be dark. The side of the Earth facing the sun is lit. The side away is dark. So I'll just draw that the obvious way, make half of the Earth dark. This is daytime, that's nighttime. Now, the moon is orbiting the Earth. Let me just put the moon over here. Way out of scale. But the moon is there. Like the Earth, half the moon's going to be lit by the sun, half the moon's going to be in the dark. So the moon is going to be like this. And again, the moon orbits the Earth. The moon goes around the Earth. I'm just saying, at this moment, the moon's right there. So we're talking about positioning. Here's the position of the sun, the position of the Earth, the position of the moon. One more thing we need the position of, and that's you. Where are you standing and looking from? Let's say you're standing right here. Obviously, that's, again, way out of scale. And you look up towards the moon. So you're looking in this direction. What are you going to see? You're going to see half the moon is lit and half the moon is dark. The dark side, you may not see at all because it's dark, but what you would see, let me put it here. You would see something like that. You'd see a half a moon. It has nothing to do with the Earth's shadow. It has to do with where are you, where's the moon, where's the sun, where's the Earth. And given those four different positions, that's going to change what you see. All right, that's one possibility. You could see a half of a moon. I know that's not a scientific term, a half of a moon, but it certainly describes what you see. Let's take another set of positions. I'm going to erase this, and it's easy for me because I can just erase it. It may be harder for you because if you want to draw it all over again, you can. All right, we said the moon goes around the Earth. Let's say the moon is over here, behind the Earth. We can assume that the light from the sun goes out in all directions and kind of goes around the Earth. It's not totally blocked. And we can certainly bring this up in class. I can give you an example of like how light isn't totally blocked. There's fluorescent light up in the ceiling here. I can put my phone like this, and you might say, all right, my phone is blocking the light. If I can put my hand right underneath it, my hand is still lit. This phone is not creating total blackness behind it because light has a way of traveling around things. And again, you can just show that, I can just show with my hand and my phone here. I can see right behind my hand because my phone's not just creating total darkness behind it. Or in this case, half the moon is going to be lit and half the moon is going to be dark. The side of the moon facing the sun is always going to be lit. All right, here's the sun, here's the Earth, here's the moon. Now let's say you're standing right here. You're on the dark side of the Earth, which means it's nighttime. And you look out towards the moon. What do you think you see now? Well, it's going to be different from a half moon. When you look up from this position, you're seeing the whole lit side of the moon. You're going to see a full moon. Because you're looking at the side of the moon that's lit from sunlight. So this little discussion was about the phases of the moon. How come the moon looks like this sometime, a half, a sliver, hardly anything? Why does that change? Because the positioning is changing. Once a month, the moon orbits the Earth. So the moon's always going to be in a different position. But that's what we said. How the moon looks depends on positions. For emphasis, let me put this down here. The moon orbits the Earth. I said a month. You know, certain months have different amount of days. January had 31 days. This month, February 2020, is going to have 29 days because it's a leap year. June is going to have 30 days. July is going to have 31 days. So when I say it takes a month, which one of those do I mean? I mean that loosely. The moon orbits the Earth in about 28 days. So if its position is changing, it's going to change what I see. That's true for any of us every day. What I see depends on where I am. I'm in here. I'm looking at the camera now. If I go open the door, I'm going to see the cafeteria. If I climb the stairs, I'm going to be looking outside. If I look over that way, I'm going to see the airport. So what I see depends on where I am and which direction I'm looking. Well, same thing out here. You go out at night or during the daytime, you look up in the sky. It depends on which way you're looking, and is the moon on the other side, or is the moon over there? Is the moon over there? Where's the sun? All that's going to change what we see. Two more things regarding the Earth, the sun, and the moon. If we say, here's the sun, and here's the Earth, and here's the moon. Again, there's a dark side and a light side, and now we're standing here. So if we just capture that moment and we look up, now it should normally be daytime because we're facing the sun. But sometimes the moon can get in the way. I mean, it's moving around. Sometimes it's going to be right in the way, and it could block the sun. That happens sometimes. It doesn't happen every year. It happens sometimes. You can Google when this is going to happen next, because this is called, this is a solar eclipse. Again, back to, what do I see when I look out at the sky? If it's daytime, well, I should say, it's not, don't look at the sun. It's really dangerous. It's really, really bright. You can cause permanent eye damage in a matter of seconds. So never, ever look directly at the sun. But if you had the right equipment, sometimes you would know, hey, the sun is being blocked out by the moon. That's a solar eclipse. Now, there's another type of eclipse called a lunar eclipse. Which will show back to the sun. Here's the Earth. Half the Earth is lit, half the Earth is dark, because half of the Earth is facing away from the sun. Now, earlier I said we don't really have to be concerned about the Earth's shadow. Just like I said, you don't have to be concerned about my phone's shadow on my hand. I mean, there's a little bit of a shadow, but it's not totally dark there. The Earth does generate a shadow. Sometimes it matters, sometimes it doesn't. As far as we're concerned on the planet, it doesn't matter to us directly because we're on the Earth. The sun's shadow would be behind the Earth and would be somewhat shaped like an ice cream cone. So the Earth really does have a shadow. Now the moon is going around the Earth. So if I say, let me change colors here. If I say here's the moon, and the moon is going this way as it's orbiting. The moon can pass into the Earth's shadow. The shadow's there. Sometimes the moon goes into the shadow. If that happens, that's a lunar eclipse. So that's another thing people can see when they go out and look at the sky. They can see a lunar eclipse. That a solar eclipse and a lunar eclipse are not illusions. They're not in the same category as a blue sky. These are real things. The moon actually does get in the way. Or the moon actually does go into the Earth's shadow. You can Google, when's the next lunar eclipse? And it'll tell you a date. I will say this, lunar eclipses happen much more often than solar eclipses. Next class we'll talk about why that is. But there's a thing called a solar eclipse, there's a thing called a lunar eclipse. One thing that's important to add is the board I'm writing on is only two-dimensional. The board is flat. Space is not flat. Space has 3 dimensions. So on the board, I can't show things that are moving in and out of the board because the board is just one surface. So this is a little bit of a simplification. But the basic idea of a lunar eclipse still holds. Sometimes the moon falls into the Earth's shadow. You can go to Google Images and just put in lunar eclipse, and you'll see a photo. The moon normally is not going to be like totally dark, but it's going to look like very much orange colored. And that's what the moon could be in a lunar eclipse. It's going to be like yellowish, and then as it goes into the shadow, it's going to look more orangey. And then as it passes out of the shadow, it's going to go back to looking more yellowish. So that's our class for today, February 3rd. There will be readings posted on D2L, which will review these topics we just went over. So please see D2L. And please do that before our next class, which is February 10th. I would imagine this class will be uploaded the next day or two, so you should be seeing this hopefully by Wednesday, February 5th. For me today, it's Monday, February 3rd, but please look at the readings, and then we'll all get together again next Monday, February 10th. Thank you for your time, and I'll see you next Monday.